Welcome to our short series on solar troubleshooting. This is going to be part one, which is sort of an overview of solar from the technician standpoint. In this presentation, we're not going to cover the installation of solar systems. We're not going to discuss in-depth technical design of solar systems. And I just want to make it clear this is not a how-to for the do-it-yourself property owners. There's a lot to be said for having a trained technician evaluate and repair your system. We need to make a few technical assumptions during this presentation. First, you have a basic understanding of AC theory, DC theory, series and parallel circuits, voltage, resistance, power, and current. We're also going to assume you can use a voltmeter to read AC and DC voltages, and you can use an amp meter to read AC current. This is a big one. I am assuming you are familiar with electrical safety and think about safety before you touch anything. We are going to be taking a look at a step-by-step approach on evaluating troubleshooting solar systems. We're going to start off with an overview of solar system types just to get us all on the same track. We're going to talk about the physically inspecting solar systems, and then we're going to move into testing two types of solar systems. Then we're going to wrap up with some possible repairs for the various conditions you'll find. You'll find that my approach is repair rather than replace when possible and financially advantageous. We're living in a throw-it-out economy right now, and solar systems have a lot of residue left over. A lot of bad things happen if you just toss them all out to anytime there's a problem. So we do want to attempt to repair first. They're also major investments. There's a number of hazards I want you to be aware of. First, trip and fall hazards. You have electrical hazards, and you have lifting and weight hazards. Trip and fall hazards is when you're climbing all over a roof or into ground-mounted panels. Just be aware of where you're at and what you can fall over. Electrical hazards are all the way through solar systems. You're dealing with upwards of 600 volts and sometimes hundreds of amps of power. Lifting and weight hazards is more when you're repairing them afterwards. You might have to lift panels, move them around while on a steep roof. Just be aware of all of this. So there's two types of solar systems. We have photovoltaic solar systems, which is PV. We also have hydronic solar systems. Photovoltaic solar is solar energy captured into solar cells that create DC power, then it is transformed to AC power. Hydronic solar is solar energy that's captured to heat. It's used to heat water, and that water is used for other uses. In this presentation, or set of presentations, we're going to primarily discuss PV solar. That's the creation of power. Just a few slides on hydronic solar, just so you get an idea of what it is. It's PVC or plastic panels, could be a pack of vacuum-packed glass tubes on a roof. They lay flat on a roof to collect solar radiation, which in turn heats the water that's being circulated through them. They're connected to a filter and a pump, usually heating a hot tub or pool, but in some cases they're tied into a water heater, like this one is. Okay. The other type of solar, which we're going to spend more time on, is PV solar. The inverter converts the DC power that's generated by the solar panel to AC that is used by most household appliances. We can't dump DC power directly into the power grill or through your outlets in your house. The inverter can be one of three types. It can be grid-tied, it can be grid-tied with battery, or it can be islanded, which is basically a standalone or off-grid system. Grid-tied inverters function along with the power grid and utility the electrical system is tied to. The output of the grid-tied inverter must match the frequency and slightly exceed the voltage being provided by the utility. The inverter has to shut down within 10 to 30 seconds, and that ranges depending on location. If the grid power is lost, that's rapid shutdown. The rapid shutdown protects the utility company line workers from having unexpected power on the lines coming from a customer's solar system. Think about it. Once that 240 volts that your solar system outputs hits that transformer on the pole, it could be upwards of 20,000 volts when it gets onto the line. That lineman, thinking that the line is dead and power shut down, could get electrocuted by that voltage from a solar system that did not shut down properly. In most solar systems, this rapid shutdown is not an overrideable configuration option. It is something that is hard programmed into the chipset. The next type of solar system we're worried about is grid-tied with battery. It has the same functionality of the grid-tied system, but also has a battery charge controller. It maintains the battery charge from solar, and in the event of power loss from the utility, it islands the electrical system and continues to provide AC current to the customers. By islanding, we mean it disconnects from the grid using a transfer switch and then shifts everything over to run from the solar system and the batteries. The grid-tied inverter has the capability of setting the correct frequency in the event of utility loss. The islanded inverter is used on electrical systems that are not tied to a utility. It has all the functionality of the grid tied with battery, but it never feeds the power to utility as there isn't one. It's used in off-grid locations and recreational vehicles and any place else where you cannot have a steady connection to a power grid. This is an example of a PV solar system. Now, we're going to talk about arrays as we go through here. Okay, you can see that this property has 1, 2, 3, 4, 5, 6 arrays on it. An array is a set of solar panels that are all tied together with the same pattern, with the same angle, and the same facing. These are all south-facing. So the different mounting options we have are ground-mounted. Panels are mounted near the ground, or better said, not on a roof. You must have open space to do this. You have to build some sort of structure to mount the panels on. Racks, if you want to say. They're easy to inspect, easy to repair problems. Roof-mounted. Panels are mounted on building roofs. Roof must be able to handle the load in the worst possible conditions. Some parts of the country that's hurricane-force winds, some parts of the country that's heavy, wet snow. The roofing material has a tendency to degrade faster being under the panels. This is due to temperature being very high under the panels. It's difficult to clean these panels, and in some cases it's extremely difficult to inspect and repair these panels. So this is an example of roof-mounted panels. You'll see that they're mounted on the roofs, and if you look closely enough at this picture, you can see that they're tied down to rails using clamps in between each panel. This is an example of a ground-mounted panel. It's a metal frame, and the panels are mounted on the frame using clamps to mount them that are screwed into the frame. There's a lot of different ways to do ground-mounted panels. But this is one array because they're all facing the same direction, they all have the same angle, and they're all tied together in series. This is another example of a ground-mounted array. You'll see that this is a metal rack, and each panel is tied to the rails on the metal rack. If you look closely at this, you can also see that there's a problem with these panels. Okay, if you look up here where I'm going to circle, maybe, there's a lot of leaves and debris on here. Now that will affect, okay, this right here, over there, that will affect power production. It's blocking sunlight. One or more PV solars, one or more arrays of solar panels. These are wired in two methods, either a string system or a micro-inverter system. A string system has a single inverter handling multiple arrays, and each array is wired in series. The DC voltages all come back to the inverter. The panels in the string systems are wired on the DC side. most often in series, with each series circuit connected back to the inverter. An aerial view of the property in the prior picture, I'll show it again, has a string system consisting of 2 inverters wired with 4 arrays. One inverter is 3.8 kilowatts per hour. The other is 5 kilowatts per hour for a total of 8.8 kilowatts per hour of solar. And here's again the example of how it's split up. Okay, we have array 1, okay, that's 10 panels wired in series. Array 2 has 11 panels wired in series. Used to have 12 panels, but there's one missing there. There was a wind incident. Array 3, okay, has 3, 6, 9 panels all wired in series. And then array 4 has 1, 2, 3, 4, 5, has 11 panels wired in series. So that's the arrays of a string panel. Arrays 1 and 2 share an inverter. Arrays 3 and 4 share an inverter. Some string systems have solar optimizers installed under each panel. The solar optimizer takes the DC voltage that the panel is outputting and either raises or lowers it to a voltage that is best suited for the string inverter. It is a DC to DC converter that tunes the panel to the system's inverter. It's good in areas where there's partial shading on part of an array or things at slightly different angles. This system does not have an optimizer, but these up here at the top are shaded early morning by these trees there. So in this case, it would be a good system to put 11 solar optimizers under those 11 panels and allow the optimizers to change the voltages out for best performance. A solar optimizer, again, is just a little device. Panel plugs in here. This plugs into the main system. We'll talk more about the plugs in a minute, but there's always one that's positive and there's one that's negative. It's DC power. You cannot confuse the two because the plugs will not connect together the wrong direction. This is a micro-inverter system. Okay, micro-inverters are great when you have 2 different facing panels. Okay, and you don't want to put them on a single inverter or on multiple inverters. Each panel, or sometimes 2, but it's most often each panel, has a microinverter of its own. The DC is converted to AC right at the panels. The cable from the roof to the collector box are alternating current. This allows different size, configuration, angles, and orientation in terms of direction, south, southwest, east, west, to work together without multiple arrays. This is an example of an N-phase microinverter. It's just a little box that has an inverter inside of it. They're usually addressable, which means they can report back individual panel power usage to a main collector. Microinverters on the back of a solar panel. Okay, they mount on the back of the panel or on the rack right under the panel, and all the power wiring from the panels is AC voltage. Okay. Just another microinverter on a panel. You have the panel connections there, and you have the microinverter there. Then there's going to be lines coming out of here, usually L1 and L2 because it's 240 volt output most often. And you put one on each cell. So if I have 60 cells, I'm going to have 60 microinverters most often. Sometimes they would do 2 cells per inverter, but most often it's 1-to-1. Then with microinverters, you have a collection box. Okay, all the power and all the different signals come down to this collection box. This is what does your rapid shutdown. Okay, this box is what shuts everything down if the utility company loses power. Then you have a fuse disconnect, and then that feeds into your main power. Inside the microinverter collection box, we usually have sets of breakers for each set of panel wiring coming in on the roof, and one main output. Looking closer, there's also usually some USB ports and stuff like that up here so we can connect into it to troubleshoot. Microinverter is a network communication. The collector box serves as a hub for this communication. It also serves as a rapid shutdown point. It's also a breaker panel for all of the rooftop AC wiring. It feeds the power into the building through the main distribution panel. String versus microinverter, why people go each direction. If there's 50% shading, okay, on a single panel, all panels on a string inverter would probably have 50% power. They don't do a great job of individual panels acting differently. A microinverter, if I have 50% shading on one panel, the remaining panels are 100%. So both sets of inverters optimize the output based on sun and shade, which is solar radiation. The microinverter does this based on the individual panel. The string inverter does this based on the array or a set of panels. The microinverter most often provides reporting panel by panel. String inverters provide reporting based on the entire array. So let's look at a 40-panel 5 kilowatt system. A string inverter, you're going to have one inverter, 40 panels, and the rooftop is going to be DC cabling. All power on the roof is going to be direct current. The microinverter, you're going to have 40 inverters, 40 panels, a combiner box for communication and rapid shutdown, but all the wire on the roof is going to be AC wiring. Okay. The example photographs are string inverters. The ones we used earlier are string inverters on my house. For my area, panels are all facing the same direction. There's natural breaks for different arrays, and squirrels that like eating wire and electrical components. The string inverters made the most sense. If my property had multiple areas of shading, panels facing different directions and angles, I would have gone microinverters. Now remember, the greater number of electrical components, the more that can go wrong, and the more expensive it is in the long run. So microinverters do provide some benefit, but also have some significantly extra components. The National Renewable Energy Laboratory lists the lifespan of solar panels between 25 and 30 years. Solar inverters are 10 to 15 years. There's degradation based on the tier, which is basically the quality of the panel. Tier 1, which is your highest quality, will degrade 0.30% annually. That's 0.30% annually. Tier 2 is slightly higher at 0.5% annually. Now remember, percent is a smaller number than actually 0.5. Tier 3 will degrade 0.80% annually. The National Renewable Energy Laboratory uses an average of 0.50% across all solar panels. This means that after 25 years, the output of solar panels may still be around 89% of the value on the data plate. Here's an example. A 320 watt solar panel, 37 volts, is 10 years old. I'm going to ignore the voltage. It's not an issue here. We're more worried about the wattage. Okay, the Tier 1 panel loses 0.96 watt per year. Again, 320 times 0.30% is 0.96 watt per year. So after 10 years, okay, we multiply this times 10 and subtract it from the 320, I'm still putting out 310.4 watts. Tier 2, loss of 1.6 watts per year. I'm going to be putting out 304 watts. Tier 3, which is the lowest quality you can possibly purchase, is a loss of 2.56 watts per year. My 320 watt panel is down to 294.4 watts. Now those numbers are not excessive, okay, but they do show that panels do degrade over time. You're going to get lower wattage output over time. The return on investment for most solar systems is 10 to 12 years. If a customer's usage habits change, do not change the savings on the solar system. They should pay for the system about 10 to 12 years. In most cases, once a customer sees the savings on their power bill, their usage has a tendency to increase. It takes a lot of discipline not to increase usage because your power bill is lower. Solar output varies with the season and the time of day. It also varies greatly with sun and clouds. Let's look at a good day and a poor day on a system. System is 8.8 kilowatts per hour. It's string inverters. There's power monitoring on both generated and consumed. And there's net metering. In other words, the power that is sent back to the grid is credited to the customer's account. So this is a sunny day. But there was a little tiny fog in the morning. The dark green line is the solar production. Okay, that's this line here. The dark green line is the solar production. And again, you can see a little bit of the fog in the morning. It was a little wavy. The light green is the energy generated. At the end of the day, it generated very close to 50 kilowatt for the entire day. Now, this is in the winter months, so the days are a little shorter. Okay. The red line is the red single line is the energy used. Okay. And then the red shaded area is the energy used accumulated. In other words, this is what is being used and bought in from the power company. So this difference between the end of the red shaded area and the green shaded area is what the power company is crediting for energy sent to the grid but not brought back in. So a closer look at a sunny day, again, used about 28 or 25 kilowatts, produced around the 50, so that difference of 25 kilowatts is given as a credit by the power company for a not so sunny day or a heavy cooling day. The same system on a cloudy day. We may have only generated 28 kilowatts. We bought in, okay, or used 32 or right over 30 kilowatts. This difference here is taken out of the credit from the other days. And at the end of the month, it's all totaled up, and you only pay for what you use. Plus, of course, the minimum customer connection fee, which is like $30. So we've talked about the different types of inverters. We've talked about the different types of systems. We touched briefly on hydro solar, but I want to spend most of our time on PV solar. We touched on net metering. We touched on lifetime and degradation. We touched on usage management. Why do I want to spend time on this whole level setting and this whole introduction? Is because you cannot troubleshoot without understanding the basics of the system. In part 2, we're going to start looking at the troubleshooting, looking for visual problems. In part 3, we're going to look at the electrical troubleshooting. And in part 4, we're going to look at replacement parts and some options to consider for repairing. Okay, if you like what you see, as always, leave comments and subscribe. And again, please remember, this is an overview and does not deal with every specific installation. There are installations that are not the norm. If you have one of those, I apologize in advance for skipping your specific system. Part 2 will be coming out shortly. Now, I do have to give a standard disclaimer here. The opinions expressed in this presentation are my own and are not those of my employer. If I say something you disagree with, blame me, not my employer. And again, to repeat, this is not a presentation designed for the do-it-yourself owner. There's serious safety concerns when servicing a solar system. Only do so if you're properly trained in electrical and ladder safety.